is Ms. DB. In this video, we will look at our beginning section on our circles chapter. In this one, we'll learn to identify tangents, secants, chords, and then we're going to use one theorem in particular to solve problems. And yeah, there's a lot of vocab in this section, so you'll want to note these words. There's an interior of a circle, which the definition of that is the set of all the points inside the circle, and the exterior is the set of all the points outside the circle. We use those words a lot within the theorems. A chord is a segment whose endpoints lie on the circle, so the segments have to be on the circle. A secant intersects a circle at 2 points, like this blue line here. A tangent is a line in the same plane as a circle that intersects at exactly 1 point. A tangent just touches the circle at 1 point, and that point where it touches the circle is called a point of tangency. Now, a chord can also go through the circle, but have endpoints here. So it could be a longer line or a ray or a longer segment. As long as there are endpoints on the circle, then you could call this segment CD or segment DC. So a chord doesn't only have to be a segment. So when we're doing these problems, you have to type the word line or segment or ray in front of these, because we don't, in Word, you don't have the tools to make a little segment or line or ray above them, so you just type the word. So here's what it'd look like if you're able to go ahead and write these. You can use for line, you can use the line symbol, which is a little line with 2 line arrows at the end, but you can also just type. Like in this first one, I did this one. It says identify each line or segment that intersects the circle, write line or segment in front of each. So for chords, there's only one chord, and it is BC. So I wrote segment BC because it can't be a line because a chord has endpoints on the circle. So you have to write whether it's a segment or a line. It could also be a ray in some cases, but none of these are. So radii, a radius goes from the center to the edge. A diameter goes through the circle, and that would be line BC. So we can have segment BC, and then later on in the same question, we have line BC because the diameter goes through the center of the circle and extends beyond. So there's both a chord and a diameter that's part of the same line. This is tangent L, that's a cursive L there. There's 2 radii, like I said, and a secant is, let's look at the definition again. A secant is a line that intersects a circle at 2 points. So we get to use line BC again for this one because it is a secant and a diameter. So one line can be several things within your problem. In number 2, there's more than one chord. Let's see, there's 2 chords. There is 1 tangent. There's 3 radii. Secant. There's only 1 secant. And of course, there's only 1 diameter. All right, then we have what circles can do. We can have congruent circles. They're congruent if and only if they have the same exact radii, congruent radii. So if they have congruent radii, then they're congruent circles. Concentric circles mean that they share the same center and they lie in the same plane. We can have tangent circles. They can be internally tangent where they touch just on one side there, or they can be externally tangent where they're touching at this point here. So they're not within, one circle's not within the other, but they're still tangent circles. They touch at just 1 point. When we have tangent circles, we can talk about some more things. We can say what is the equation of the line at the point of tangency. So you can see here that we have 2 internally tangent circles, and the point of tangency is this point right here where the 2 circles touch. So you'll have to find the coordinates of that point. That point is at 1, 2, 3, 0. X is 3, y is 0. And then you have to write the equation. So vertical lines always have the equation x equals and then whatever they go through. So this one's going through, of course, at the point of tangency, so it'd be x equals 3. If you have a horizontal line, it's y equals the point that it goes through. So it'd be the y value of the point of tangency. So you have 3 examples where you're going to do these. In number 3, here's your 2 externally tangent circles. Here's your point of tangency. You need to write the coordinates of that point, the x value and the y value. So it's 3, 2. Oh, it asks you to find the length of the radius of each of them. That's just a little practice. This one's radius would be 2 units long, and this one has a radius that is 1 unit long. Coordinates of the point of tangency, and then the equation of the tangent line at the point of tangency. They already drew that line in. It's this line here. So your job is to say what is the equation. I already wrote that it's going to be x equals something, so you need to figure out what does that equation, where does it go through the x-axis. And then number 4, we also are asked to find the length of the radius of each circle. Again, that's just a little bit of practice. The coordinates of the point of tangency, and then the equation of that tangent line. You can have a common tangent, and that is a line that is tangent to 2 circles, or it could be more circles. So we have in these 2 circles that are separated this way, we could draw 2 tangent lines, one above, one below. We could also make tangent lines like between them, like an X shape. So it would have 4 common tangents. All right, now we get some theorems. The first one says that if a line is tangent to a circle, then it is perpendicular to the radius drawn at the point of tangency. So right here, that point of tangency, we would have perpendicular radius and tangent line. If a line is perpendicular to a radius at a point on the circle, then the line is a tangent. So if you know that this is perpendicular, then you know that this is a tangent. So it works both ways. One is the converse of the other. Now here's the theorem we're going to use quite a bit. It says if 2 segments are tangent to a circle from the same external point. So if you have this external point and you draw a line tangent to the circle here and tangent to the circle here, these segments are congruent. We will use this a lot because if these 2 segments are congruent, then and you have an expression for each of them, then you can set up an equation, solve this for x, and then find the length of the segments. Now the segments will be congruent, so you only have to find one of them and then you'll know both of them. So to solve this for x, let's see, I'll subtract 1x from both sides. 2x minus 1x is 1x, so 3 is equal to x, or 3 equals 1x. So now that I know what x is, I still have one more step, which is to find what segment BC is. So I take the 3 and plug it back into BC. So BC is equal to, I'm going to try to get that up a little bit here, so it's on the same page as the rest of the problem. So BC is equal to x plus 3, but now we know that x is 3, so you know that BC is equal to 6. And you have several of those questions to do. Here's another one. This one you're looking for y, and then you'll find the length of LM. And number 8, you're looking for y again, and you'll be looking for segment RS, and so on. Number 10 is just a little bit different because there's an x squared. Almost always when there's an x squared in a problem, you will get a quadratic equation, which means you'll have 2 possible solutions. So we start again by setting them up equal to each other using that theorem. Now we have divided by 2. The opposite of dividing by 2 is to times by 2, to multiply by 2. So I'll multiply both sides by 2. So I get 10x, 2 times 5 is 10x, equals, these cancel, x squared. Now you can't just do magic and say what the answer is. So what we're going to do is set this equal to 0. I'm going to subtract 10x from both sides. So now I get 0 is equal to x squared minus 10x. And I kind of like it better on the right side, so I'm going to rewrite this. Now I'm going to look for common factors in these two terms. They both have an x common. X squared divided by x would leave me with 1x, and minus 10x divided by x would just leave me with minus 10. And then the zero factor theorem says that one of these must be 0. So either x equals 0 or x minus 10 equals 0. Solve this one. So I have two answers. I have x equals 0 or x equals 10. Does it make sense for x equal to 0 here? Then I would get 5 times 0 is 0 for the length of this. It doesn't really make sense. So I'll use this one, x equals 10, and then you still have to plug back in to find the length of, I have to write where, let's find the length of GE. And the length of GE should be equal to EF, so let's check both of them. GE would be 5 times 10, or 50. EF would be 10 squared, so 10 times 10 is 100, divided by 2, which is also 50. So you'll get the same answer. Number 11 is a word problem about a bike, and the bike is spinning. And as it picks up dirt or water, it'll spray, and it sprays this far in that little tangent segment. And you just have to find the length of that. So you just can use the Pythagorean theorem to find the missing leg. In the last section, you're going to read these, look through the definitions in the book and the theorems that are on the worksheet and in the book, and decide whether these statements are sometimes true, always true, or never true. All right, that's it. Thanks a lot and have a wonderful day.